So the topic of the videos for section 4 is really on tangent lines. We talked a little bit in class about rates of change. We need to learn a little bit more about tangent lines, and then we're going to connect the two together. So I want you to consider the following drawing. We have an upside down parabola. Let's say that I wanted to find the slope of the tangent line through this point. So I want to find the slope, even in the end if I want to find the equation of that point, I need to know the coordinates. Let's pretend I know those, and I need to know the slope of that red line. That's going to be a little hard at this point because I only know one point. However, if I were to add a second point into the picture, now I can use those two known points to find the slope of this blue line. So the red line is a tangent line. The blue line, the one that connects 2 points, we call a secant line. And so the goal of this lesson is to basically set up a slope formula for the blue line, and then using limits, we're going to use it to find the slope of the red line. And then once I know the slope and I know the coordinates of that point, then I'm going to find the equation for the tangent line. And just a heads up, remember that way back from Algebra 1, we have this sort of equation, y equals slope times x minus x sub 1 plus y sub 1. Or maybe a more familiar version of that would be y minus y sub 1 equals m times x minus x sub 1. Just our point slope formula, we're going to be using that at the end of this lesson to find the equation of our tangent line. So here we go. So let's pretend we had just a function f. We're just going to be looking at a parabola right now. And we know the coordinates for this. We're using variables. Just pretend we actually know the coordinates. So our x value is a, and so the y value that goes with it would be whatever we get when we plug in a into function f. So these are our coordinates right there. Our goal is to find the equation of the line tangent to the function at point A. We want to find this. We already know the coordinates, we just need to find the slope here. So that's kind of our goal. The problem is our slope formula requires that we use 2 points, and so we're going to use the idea of a secant line in the end to get the slope of our tangent line. So let's pretend that we're going to add another point to this picture. We're just going to move a certain amount over. Let's say that we pick a point right about there, so that's going to line up. Maybe that's a little too far. Let's see if I can erase here a second. There we go. We'll make our new x value right there. And we're going to move to the right a little bit, and we're just going to call the amount right in here, we're just going to call that h. So if that is a distance of h to the right, that means that this must be an x value of a plus whatever h is. So lots of variables here. I know it's a little bit of a pain, but that's kind of what we're looking at. Okay, we're going to have a point that matches up right there, and the coordinates for that would be, let's see here, those coordinates would be an x value of a plus h, and then we plug that into our function f, so the y value is f of a plus h. And now I can use those points to come up with a secant line right through there. So let's try to find the slope of that secant line a second. So remember, slope is y minus y over x minus x. And so if we think about that, we would really end up with y minus y. So here's our y value minus the other y value. We're kind of thinking of this little piece right in there, what's y minus y. And we get f of a plus h minus f of a. And then on the bottom part, x minus x, here's our x values that we're interested in, or we're kind of looking at this part right there. We would have a plus h minus a, and that's going to simplify for us. And so a simpler way of writing that would just be in the numerator f of a plus h minus f of a all divided by h. And that's basically the slope of the blue line that we have there. But remember, we really want to find in the end the slope of the tangent line. It's going to go like this. So how do we get this blue line to get closer and closer to the tangent line? Ideally, we would take this point and we just keep moving it closer and closer and closer to our fixed point of A, because really we want to find the slope of our tangent line at A. So what's controlling this movement? Okay, what's controlling the movement is h, whatever distance we picked. If I can move this thing closer and closer and closer to letter A, or to point A, that's going to take this entire point and move it closer to our original point, and that's going to get us closer to a tangent line. That's the whole idea of derivatives, which is really the main topic of our entire first semester. So all I'm going to do to this general rule is just put in a limit as h approaches 0. Okay, that's the big point for today's lesson. We're going to call this the difference quotient, and it's the method for how we come up with the slope of a tangent line. Now, one thing to notice right away, whatever, I'm going to be filling some things in here depending on what the function is. But h will always be in the denominator, and I'm never going to be able to substitute 0 in right away because I divide by 0 and we don't like that. So we're going to have to work on doing some algebra to simplify this once we have a specific function that we're looking at. Okay, this just kind of summarizes everything we mentioned. Here is our general rule up here. Slope of a tangent line is going to equal this thing. We call it the difference quotient. We need to simplify first, and we have simplified it when we do algebra the right way, where we can finally cancel that h out in the denominator. So this is kind of the basis for our entire first semester. We will learn more things about this in the rest of this unit, but then luckily the rest of chapter 3 gives us shortcuts for this entire method, so it won't look as messy for the majority of class.